unfold.
Welcome to the Deep Dive. Today, we are staring down what is essentially the ultimate planetary time bomb. The Thwaites Glacier.
Right.
You've probably heard it called the Doomsday Glacier. And frankly, after going through the stack of sources we have from the 2024 and 2025 field seasons, that nickname, it feels less like hyperbole.
Yeah, it feels more like a precise description of the threat.
It really does. Okay, let's unpack this. We are talking about a colossal expanse of ice in West Antarctica. So large, it's comparable to the size of Florida.
Or the entire island of Great Britain. It's just immense, an ice stream of almost unimaginable proportions.
And our mission today is to go far beyond just the headlines. We're going to synthesize the most urgent in-the-field findings, especially from the big one, the International Thwaites Glacier Collaboration, the ITGC.
And the key takeaway from all these latest sources is a deeply unsettling one.
It is.
This massive system is moving away from that slow, expected, linear process of thermal erosion.
It's simple melting.
Simple melting, exactly. And it's moving into a rapid, nonlinear phase of what we can only call structural shattering.
That structural shift, that's the thing that changes everything.
It is. It's the critical variable that changes the entire risk assessment for the next century. And, frankly, for the next few decades. Thwaites isn't just a big glacier.
No.
It holds a very specific geophysical function. It acts as the singular cork.
A plug.
A massive plug, yeah, holding back the entire West Antarctic ice sheet of the ways. If that cork fails, the rest of the ways is severely compromised. It triggers a cascade that, the glaciologists have been fearing for half a century.
And the stakes, which we have to lay out right up front, are catastrophic. We're not talking about a few inches of sea level rise here.
Not at all.
The sources make it undeniably clear. The removal of this cork would trigger an ice discharge capable of raising global sea levels by over 3.3 meters.
Which is roughly 10.8 feet.
10.8 feet. Just think about that number. For most major global coastal cities, that's the difference between having storm surge protection and just permanent inundation.
And while the full drainage is measured in, centuries, the structural failing of the buttressing ice, the part that prevents that catastrophe that's happening now,
right now,
the countdown for a major acceleration is no longer theoretical. It's being measured in decades.
So to understand why this feels so sudden, we have to go back. We have to understand how recently this entire area was, for all intents and purposes, invisible to us.
That's right. For centuries, the whole MICI sector, which is where Thwaites sits, it remained this completely remote and unknown region. The story really begins with just pure geographical curiosity.
It's fascinating how our own human limits defined how we saw the continent for so long. Our sources trace the very first recorded approach way back to Captain James Cook.
January 1773. He was commanding the HMS Resolution, and he sailed further south than anyone had before him, pushing right up to the edge of the permanent ice.
And he hits a wall.
He hits a wall. He reached what he called his ne plus ultra, his no further point, somewhere near 71 degrees south. And he was stopped cold by what he wrote down in his logs as an immense ice field.
An immense ice field. And that vast, impassable wall of ice, it basically defined the southern limit of human navigation for over a century?
Well over a century. And that physical limit led to a kind of geopolitical vacuum. The Amundsen Sea remained the only sector of Antarctica that was never claimed by any nation.
Why? Just because it was so hostile?
Exactly. It was too remote, too packed with sea ice. Nobody could get in there to plant a flag. And that sheer physical remoteness, it protected its geological secrets. It kept this incredible instability hidden from us.
So the first real human glimpse of that specific coastline only came much, much later.
Much later. The sources pinpoint the Antarctic summer of 1940. This was during the U.S. Navy's massive post-World War II mapping endeavor called Operation High Jump.
Right. They used aircraft launched from carriers.
They did, to map the entire coastline. And that gave us the first aerial, comprehensive perspective of what was only identified decades later as the, quote, weak underbelly of the Antarctic continent.
And even after they mapped it from the air, it still took, 2 more decades for the glacier to be formally defined and even get a name?
Yeah, that happened between 1959 and 1966. And here's that small, slightly ironic historical footnote you brought up earlier.
Right. It was named after Frederick T. Thwaites. He was a glacial geologist at the University of Wisconsin-Madison.
And the man whose name now defines one of the biggest global coastal risks.
Never set foot on the continent.
Never once. And that little detail, it really encapsulates the historical disconnect. For most of the 20th century, the prevailing view in glaciology was that all Antarctic ice sheets were lethargic giants.
Slow, unchanging.
Exactly. They were thought to respond to climate forcing over tens of thousands of years. Millennia. The idea of a rapid century-scale collapse was, it was basically science fiction to most experts at the time.
Which brings us to that crucial paradigm shift.
Yeah.
The 1970s and 80s. This is when the initial fuse was identified. And the sources all point to one key figure, glaciologist Terry Hughes.
In 1981, Hughes published this groundbreaking hypothesis. He suggested that the Pine Island Glacier and the Thwaites Glacier were interconnected, and that together they constituted this highly vulnerable, weak underbelly of West Antarctica.
He was sounding an alarm that almost nobody was ready to hear.
Pretty much. But he wasn't just guessing. He identified the crucial defining feature of the entire region.
That the West Antarctic ice sheet is a marine ice sheet.
That's the key. That's the difference between this and, say, East Antarctica. WAIS is grounded on bedrock that is significantly below sea level, sometimes kilometers deep.
So Hughes's theory was revolutionary because it laid out a mechanism for rapid collapse.
It did. He posited that if the floating ice shelves at the coast, which act as a brace, that cork we mentioned, if they were melted or removed, the entire inland sheet, even though it's resting on the ground, could just rapidly drain into the ocean.
But the tech wasn't there yet to prove him right. The initial reaction was what? Skepticism.
A lot of skepticism, yeah. Partly because the early satellite images, they were just too low resolution to really capture the instability.
The Landsat program images from the 80s.
Right. They couldn't penetrate the ice. They couldn't measure the subtle shifts in flow velocity with enough precision. In fact, some of those early analyses even seemed to suggest the ice sheet was holding steady. So the urgency of Hughes's theory was, it was largely dismissed until the next generation of technology came along.
Which takes us to the real turning point, the radar revelation of the mid-1990s.
This is it. This is when we move from hypothesizing a risk to actually identifying the bomb and starting the timer.
And this was all thanks to the European Space Agency.
Yes, and their deployment of synthetic aperture radar, or SAR, interferometry. This technology, it just changed everything. It used satellite radar echoes to measure ice velocity with millimeter precision.
And crucially, it could see through the permanent darkness of the polar winter,
which gave us a continuous high-fidelity view for the first time.
And the scientist who made the definitive finding using that data was glaciologist Eric Rignot. He was the one who could finally peer beneath the veil.
Rignot's analysis was a monumental piece of work. He used that millimeter precision data to pinpoint the exact location of the grounding line.
That's the critical threshold where the bottom of the glacier lifts off the bedrock and starts to float.
Exactly. And the data confirmed Hughes's darkest predictions. The grounding line was not static. It was retreating rapidly inland, and it was accelerating the flow of the ice above it.
And what's so fascinating is how this technological confirmation lined up perfectly with some critical oceanographic data that came out at almost the same time.
It was the perfect confluence. In 1994, Adrian Jenkins and Stanley Jacobs, they led an expedition. They sailed the icebreaker Nathaniel B. Palmer right into Pine Island Bay. And what they found there was the key. Inexplicably warm water. Warmer and saltier than could be explained by local surface effects, and it was circulating beneath the floating ice shelves. Suddenly, the whole picture just coalesced for the scientific community.
The ocean was eating the ice from below,
creating the exact geometry Hughes feared, and the ice was responding by flowing and retreating faster.
So Rignot's 1997 paper, that was the moment.
That was the moment. It shifted the consensus from slow stability to imminent collapse. The sources are incredibly clear about this. This is when the bomb was identified and the timer officially began ticking.
An incredible story of how technology revealed a danger that was hiding in plain sight. But identifying it isn't enough. We need to understand the physics of the bomb itself.
Right. The geology, the structural mechanics, all the things that make Thwaites uniquely dangerous.
Here's where it gets really interesting. This is a system that seems almost perfectly designed for catastrophic failure.
The term Doomsday Glacier, it really does stem from this specific geological and geometrical configuration. Thwaites is what we call an outlet glacier.
Meaning it's the main drain for a huge basin behind it.
The primary, most powerful drainage system for a massive, deep interior basin within the WAIS, yeah.
So let's nail down that cork mechanism. The rest of the WAIS is millions of cubic kilometers of ice sitting on land that's below sea level. Thwaites is the plug holding it all back. What makes this specific plug so effective at holding, but also so dangerous when it lets go?
It's just defined by extremes. As we said, Thwaites is the widest glacier on Earth. We're talking about a flow path that is roughly 120 kilometers or 75 miles across at its mouth.
And that massive width, that gives it a huge surface area for the ocean to attack.
An immense frontage, yeah. It maximizes its exposure to the warming ocean water and to the tidal mechanics that we're going to get into later.
And the catchment area, the giant bowl it's draining,
Yeah.
it gives you a sense of the sheer volume involved.
Its catchment area is 192,000 square kilometers. That is, as you said, the size of Florida. It contains a huge, vast portion of the interior ice sheet.
And the thickness is just
Yeah.
hard to comprehend.
The sources indicate the ice thickness ranges from 2,000 meters up to 4,000 meters in places. That is a colossal column of frozen water. I mean, just think about the potential gravitational energy contained in that volume, all of it driving the flow toward the ocean.
But the single most dangerous feature isn't the size. It's the shape of the land underneath it. It's the geology that facilitates the core mechanism of collapse. Marine Ice Sheet Instability, or MII. We have to really explain this retrograde slope.
This is the physics that guarantees once retreat begins, it becomes a runaway process. Retrograde slope just means the bedrock gets deeper as you move inland from the coast.
So it slopes down, away from the ocean.
Exactly. It descends from about 800 meters below sea level to well over 1,200 meters. And this specific geometry creates a self-sustaining, disastrous feedback loop.
Okay, let's break that down. Why is that deepening bedrock so catastrophic?
Well, the simple analogy is that the ice is like a huge piece of stiff putty being squeezed by gravity. When the grounding line retreats into deeper water, the column of ice immediately above that point becomes thicker, just because the seafloor is further below the surface.
Right.
And according to the fundamental physics of how ice flows under stress, thicker ice experiences greater internal pressure, and therefore it flows dramatically faster.
So thicker ice flows faster.
Which in turn leads to a faster retreat of the grounding line.
And that faster retreat exposes even deeper bedrock.
Which leads to even thicker ice, and the cycle just accelerates. It becomes exponential. Thwaites isn't just, susceptible to AIs. It's cited in glaciology textbooks as the single most dangerous textbook example of a system primed for this kind of runaway failure.
So that explains the large-scale structure, the volume, the catastrophic geometry. But the really recent observations from 2024, they revealed the hidden plumbing system that's accelerating the melt. These bedrock channels.
The ocean's express lane, yeah.
Exactly.
This is a crucial recent discovery, and it was only possible because of these sophisticated radar and seismic surveys. They showed that the topography beneath the ice, it's not a smooth, predictable slope.
No, it's jagged.
It's a complex network of jagged troughs, deep depressions, and canyons that have been carved into the bedrock. And these features, they serve as perfect hydrodynamic funnels.
And they funnel the one thing you don't want there. Warm water. The circumpolar deep water.
Directly to the most sensitive areas. The 2024 field observations were able to map a network of 800-meter deep trenches. This depth is critical.
Why?
Because it allows that relatively warm CDW to penetrate not just beneath the ice shelf, but deep inland. We're talking up to 60 kilometers beneath the floating ice shelf. These deep channels completely bypass the shallower protective ridges that might otherwise act as natural buffers.
So the ocean has basically found the perfect deep water route to erode the core structural support of the glacier.
That's it. So, the physics is just stacked against us. The glacier is massive. It's sitting on a reverse slope. And now we know that the bedrock itself is grooved with these huge channels that deliver the heat right where it can do the most structural damage. This confirms why all the new data is so worrying.
Which brings us to the detonator.
This is the section where the whole narrative shifts from theory and, gradual melt rates to imminent mechanical breakdown. The observational data from the 2024 and 2025 field seasons, it has fundamentally changed the scientific assessment.
We're not talking about slow melting anymore.
No, we are no longer discussing slow thermal retreat, which is a linear process. We are discussing nonlinear mechanical structural failure. The ice isn't just melting slowly from the bottom, it is structurally shattering.
And the most visible evidence of that shattering is the state of the Thwaites eastern ice shelf, the TICE, the spiderweb fractures.
That's right. High-resolution satellite imagery, advanced aerial reconnaissance, they have documented the rapid and dramatic propagation of these fractures right across the Tees. And you have to remember, this ice shelf is structurally critical.
It's a break.
It's a massive hydraulic break. It provides backstress, slowing the flow of the colossal ice stream that's sitting behind it.
But it's failing in a way that is structurally more dramatic than anyone expected.
It's described precisely as shattering, which is a brittle failure mode. It's physically faster than the viscous slow flow of ice. The cracks are forming this distinct, complex zigzag pattern.
What does that pattern tell you?
It indicates that the cracks are connecting pre-existing flaws and weaknesses within the material. This confirms that the internal stress of the shelf, the pressure from the huge ice stream pushing on it, has finally exceeded its actual material strength.
So it's breaking apart.
It's converting from a cohesive, solid barrier into basically a collection of loosely connected blocks of ice.
And what does that do to the timeline for the final failure of that shelf?
Well, the sources convey a severe and urgent warning. Researchers now believe the final, catastrophic disintegration of the ties could occur within the decade.
Within the decade?
Or potentially even sooner. It depends on the intensity of the upcoming Southern Ocean heating cycles. This is a significantly contracted timeline compared to the earlier estimates that only accounted for thermal melting. The structural integrity is failing far faster than the mass is melting.
And a key element holding that shelf together was the pinning point. This underwater mountain that was acting as an anchor. Is that anchor finally giving way?
The 2025 reports confirm the worst. The Thwaites is fundamentally losing its grip on this crucial feature. For decades, the pinning point created friction, providing essential stability.
And now?
The current detachment process, it's been categorized by researchers not as a sudden break, but as a 20-year fracture cascade.
A 20-year fracture cascade. So this has been building for a while.
Slowly building and accelerating for 2 decades, yes.
Can you walk us through how that cascade works? Because it sounds like a self-fulfilling prophecy of failure.
It is a textbook feed-forward loop. It's all driven by that warm water. The basal melting causes the ice to thin. The thinning ice eventually lifts off the pinning point, like a wet sheet lifting off a rock.
And as soon as friction is lost,
the massive ice stream behind it immediately accelerates. That acceleration stretches the remaining ice, which creates more tension and new fractures upstream. Those new fractures further weaken the shelf, which increases the flow and the stretching.
It's a runaway process.
It's a runaway, self-sustaining process where the anchor itself is now becoming the focus of its own destruction. The ice is ripping itself apart, trying to flow over or around it.
So we have that top-down satellite view of the failure, but we also have, arguably the most exciting in-depth data, thanks to the revolutionary findings from the autonomous underwater vehicle, IceFin.
An incredible feat of engineering and endurance. It really was.
Just getting it. It must have been a logistical nightmare.
Absolutely. IceFin, which is a long, pencil-shaped AUV, it was deployed through a 500-meter borehole drilled directly through the solid body of the glacier.
Just to get into the hidden ocean cavity underneath.
And what it found there fundamentally defied the simple, smooth geometry that glaciological models had relied upon for years.
The expectation was a relatively smooth ceiling, right? Just created by uniform melt.
And the revelation was this upside-down landscape. IceFin found chaotic, complex topography, stair-step terraces, deep inverted canyons, huge crevasses carved out by powerful meltwater plumes. This discovery, it just fundamentally alters how scientists must now model basal melting.
Why does that chaotic, inverted topography matter so much more than a smooth ceiling? It feels counterintuitive that more texture would accelerate the melt.
It all comes down to fluid dynamics and turbulence. IceFin found that the melt rate on the flat, smooth sections of the ice base was actually lower than expected.
Really?
Yeah, possibly because a thin, insulating layer of fresh meltwater just sits there and accumulates. But the complex shapes, the deep crevasses and the steep faces of those terraces, they created immense turbulence in the water flowing beneath the ice.
And turbulence means mixing.
Exactly. This turbulence actively mixes the warmer, saltier circumpolar deep water right up against the ice surface. And that drives incredibly high melt rates, but it targets them. It's happening exactly in the geometry that is weakest.
So it's a structural, targeted melt. It's not just sanding down the bottom.
It's exploiting the glacier's internal flaws. And the sources confirm the ultimate danger of this targeted attack.
Which is?
Ice fins specifically observed warm water funneling directly into those basal crevasses, widening them and actively driving fractures upward into the thick, solid body of the glacier.
So it's attacking from below.
It's a process glaciologists now call basal rifting, and it confirms that the glacier is under a structural attack from below, not just a gradual thermal sanding. It's being attacked at its seams at the same time as it's being shattered from the top by its own internal stress.
We've established the structure of the bomb and the mechanical detonator that is now active. Let's look at the accelerant. What is constantly fueling this explosive disintegration?
The primary agent of destruction, the fuel for this whole system, is oceanic heat. Specifically circumpolar deep water, or CDW. This is the heat source that makes everything else possible.
How warm is this water, really, and where does it come from?
Well, it's only relatively warm. It's usually measured at about 1 to 2 degrees Celsius above the freezing point of the surrounding surface water. But you have to remember, ice requires a massive input of energy just to change its state.
So even that small difference is huge.
It's sufficient to melt meters of ice per year. And where it comes from? Well, it's part of the global thermohaline circulation. It actually originates as North Atlantic deep water that has circled the globe.
So this is a truly global heat source being delivered to this one spot in Antarctica.
It is, and normally it's kept away from the continental shelf by the powerful Antarctic circumpolar current. That's the barrier.
But changing climate dynamics are breaking down that barrier. They're forcing that deep, warm water inward.
That's the tragic nexus of global and regional climate forcing. You have changing wind patterns, driven by the combination of the partial recovery of the ozone hole and the general intensification of what's called the southern annular mode due to global warming.
And these winds are pushing the water.
They're forcing this warm, deep, saline CDW up onto the shallow continental shelf. And from there, it flows directly into those 800-meter deep troughs beneath Thwaites that we just talked about.
And the 2024 observations, they are definitive that this invasion is happening, and it's vigorous.
They confirmed it. This warm water is circulating vigorously, pouring through those trenches and delivering immense, relentless melting energy directly to the grounding zone and to those basal rifts. It's a continuous high-volume heat delivery system.
Beyond just the continuous heat supply, there's a mechanical process that actually turbocharges the melt. This bellows effect, the tidal pumping.
This is a fascinating finding from the ITGC campaigns, one that really highlights the nuanced mechanics of the collapse. It confirms that Thwaites doesn't have a precise, fixed grounding line. It has a grounding zone.
A zone, a wider area.
A wide area, sometimes kilometers wide, where the massive ice slab actually floats when the tide is high, but rests firmly on the bed when the tide is low.
And that daily movement is the bellows, forcing the water where it doesn't belong.
Exactly. As the tide rises, the gargantuan weight of the ice slab is subtly lifted. This action physically pulls warm, high-pressure seawater kilometers inland into that newly opened space between the ice and the bedrock.
And then the tide goes out.
The water flushes out, but the immense heat has already been transferred to the ice base.
So it's not just melting the ice, it's also acting as a lubricant.
Critically, this daily tidal process, it acts like a massive diaphragm pump, mechanically forcing heat into the most vulnerable structural areas. But at the same time, it lubricates the bedrock, reducing friction dramatically.
And less friction means a faster slide.
Exactly. This reduced friction is precisely what allows the glacier to slide faster, while the heat ensures the ice is melted from the bottom up, further thinning the ice shelf and hastening the loss of that pinning point.
So we have the Southern Ocean supplying the heat, and the tides mechanically pumping it inland. We also have to connect this to global atmospheric patterns, specifically El Niño. How tight is that link?
The research published in 2023 and 2024 has successfully established a clear teleconnection between the stability of Thwaites and the El Niño Southern Oscillation, or ENSO.
It shows how globally interconnected this whole system is.
It really does.
So how does El Niño in the Pacific affect a glacier in Antarctica?
It all comes down to wind patterns. During an El Niño event, the trade winds in the Pacific weaken and shift. This, in turn, alters the prevailing westerlies around Antarctica. And these altered wind patterns, the sources describe them as unstacking the normal water layers, they facilitate the crucial upwelling of that warm CDW onto the continental shelf near the Amundsen Sea.
So El Niño basically acts as a periodic, highly efficient delivery service for the heat source.
Precisely. And this is the whirling extrapolation from that. Since global climate change is increasing the frequency and the intensity of major El Niño events, we can anticipate a more consistent and more intense heat supply being delivered to the grounding zone of Thwaites.
Guaranteeing recurring pulses of acceleration.
Exactly. It's a global climate pattern directly exacerbating a local geophysical crisis.
The structural breakdown is accelerating, fueled by global heat and mechanical pumping. Let's review the two primary collapse mechanisms that glaciologists are tracking, and, more importantly, let's quantify the truly terrifying global impact.
The first mechanism is Marine Ice Sheet Instability, MISI, which we've spent some time on. This is the failure mode based on that reverse slope geometry. It is active and it is ongoing.
Meaning the glacier retreats into deeper water, the grounding line thickens, and the ice discharge just increases exponentially. And the evidence that MISI is driving the current crisis it's overwhelming.
It's the established reality. The grounding line has already retreated 14 kilometers since those initial Renault findings in the 90s, and the total ice discharge rate has effectively doubled over that time.
And the loss of the pinning point is removing the last real obstacle.
The recent structural breaking up and the eventual loss of that critical pinning point on the eastern ice shelf is removing the last significant obstacle to a rapid, irreversible MISI phase.
Yeah. The second mechanism is potentially even more catastrophic and leads to a much faster timeline, though maybe slightly less certain. Marine Ice Cliff Instability, or MICI.
MICI is based on the physical limits of ice strength itself. The theory says that once the floating ice shelf is completely gone, it leaves behind a massive, sheer, vertical ice cliff at the grounding line.
A wall of ice.
A huge wall of ice. And since ice is a brittle mineral, it has a physical yield strength. If that cliff exceeds roughly 100 meters above the water, which implies a total ice thickness of around 900 meters or more, the stress at the base of that cliff exceeds the material strength of the ice.
And it just fails instantly.
Correct. It leads to a rapid domino-style collapse. Massive sections of the cliff calve off and slump into the ocean, which immediately exposes a new, even taller cliff behind it, leading to continuous high-speed retreat.
But the sources note a crucial nuance from the 2025 modeling.
Yeah.
MICI might be less inevitable than we thought.
Right, but not because the cliff is stable, it's because the thinning is so fast.
So we're trading one disaster for another. If the basal thinning is reducing the cliff height, does the faster basal melt from the ice fin dynamics? Does that guarantee a faster overall collapse via MISI, even if the cliff doesn't reach that critical collapse height?
That is the essential question the researchers are debating. Rapid basal thinning might reduce the cliff height below that critical 100-meter threshold, thereby preventing the explosive MICI retreat. But at the same time, that rapid loss of mass, combined with the loss of the pinning point, only accelerates the rate of ice flow and the NSI failure.
There's also this idea of an ice melange.
Yeah, a stabilizing ice melange. It's basically a thick collection of broken icebergs that get jammed into the bay. And that could provide enough back pressure to temporarily slow the cliff collapse. But regardless, MISI alone is sufficient to drain the entire basin.
MICI would just drastically speed it up.
It would accelerate the timeline to mere decades.
Either way, the volume is massive. So let's move from glaciology to cartography and actually quantify the sea level rise scenarios.
The figures are truly staggering. If only the current volume of the Thwaites Glacier fully drains, it contributes 65 centimeters, or about 2.1 feet, to global sea level rise.
Over centuries, but at an accelerating rate.
An accelerating rate, yes. The ultimate threat, the existential one, is the full collapse of the entire West Antarctic ice sheet, which is triggered by the loss of Thwaites. And that holds a potential rise of 3.3 meters.
10.8 feet. And Thwaites is already a major contributor right now.
Yes. Even in its current phase, Thwaites contributes roughly 4% of the global sea level rise annually. So its current acceleration is already a major factor in coastal management plans globally.
But the distribution of that rise it's counterintuitive because of this gravitational physics that most people never consider.
The gravitational fingerprint. This is a critical insight for understanding the blast radius.
It's essential physics. Ice sheets are so unimaginably massive that they exert a significant gravitational pull on the surrounding ocean water, drawing it toward them.
And when Thwaites melts, that massive gravitational field diminishes and eventually vanishes.
So the water that was being held near Antarctica actually flows away.
Exactly. Sea levels near the melting ice sheet actually fall because of the loss of that pull. That enormous volume of water is then redistributed globally.
And the physics dictates that this redistribution causes coastlines in North America, Europe, and Asia to experience a higher than average sea level rise from the collapse of Thwaites,
which magnifies the threat to these densely populated regions. The risk is essentially imported to the northern hemisphere.
The 3.3-meter threat is no longer theoretical, so we need to make it visceral. Let's look at the urban impact case studies in the source material, starting with London, which relies on a massive defensive structure.
London's primary defense is the Thames Barrier, operational since 1982. It protects 125 square kilometers of vital infrastructure. We're talking Parliament, the tube network.
And when it was designed, it was expected to close, what, 2 or 3 times a year?
During exceptional high tides and storms, yeah. But its operational limits are already being severely tested. In the winter of 2013-14 alone, the Thames Barrier had to close 50 times.
50.
50 times. That is nearing its hard operational limit before critical maintenance cycles start to fail. The city's official planning document, the Thames Estuary 2100 Plan, it anticipated upgrading or replacing the barrier by 2070.
But a Thwaites acceleration would render that timeline completely obsolete.
Decades ahead of schedule. The sources note that a failure or a breach wouldn't just flood residential areas, it would cause an unprecedented economic shock by flooding the London Underground and critical financial infrastructure. The city is playing catch-up against accelerating physics.
And then across the Atlantic, New York City faces an even more complicated dual calamity.
New York is an archipelago city. It has over 520 miles of densely populated coastline, but it faces the twin threats of rising seas compounded by local land subsidence.
The land itself is sinking.
The land is sinking due to a geological process called glacial isostatic adjustment. So lower Manhattan, vast sections of Queens and Brooklyn, they sit only a few meters above current sea level.
The impact of a 3-meter rise there would be almost total devastation to the infrastructure that makes the city function.
It would permanently inundate the historic Battery, the entire financial district, and critical entry points of the subway system, which is already struggling with present-day flooding. Critical logistics infrastructure, like JFK and LaGuardia airports, both built on fragile coastal wetlands, they face existential threats.
So the existing resilience measures, like the Big U seawall, they're designed for inches, not meters.
They're designed for incremental rise, not a multi-meter disaster.
And finally, we have to look at Shanghai, which the sources call arguably the single most vulnerable megacity on Earth to this specific threat.
Shanghai is critically exposed for 2 reasons. First, it's located on a soft alluvial plain at the mouth of the Yangtze River. Second, and crucially, the city is actively sinking.
More subsidence.
Not just from sediment compaction, but also from decades of aggressive groundwater extraction, which significantly exacerbates the sea level rise problem. The ground level is moving down while the sea level is moving up.
What happens in a 3-meter scenario there? What is the human and economic cost?
That rise would permanently submerge the historic Bund and the glittering Lujiazui financial district, turning the city's heart into a lagoon. The economic fallout from losing the world's busiest container port would be incalculable.
And the human cost.
Staggering. Projections linked to a waste collapse scenario suggest Shanghai could be completely gone, displacing up to 17.5 million people in that region alone. The blast radius of the Thwaites failure is genuinely global. It redraws the map of human civilization.
Given that scale, the accelerating timeline, the devastating impact, the conversation has shifted dramatically. We've moved from passive observation to the active debate over desperate Plan B geoengineering interventions.
That shift itself is a profound tacit acceptance by world leaders and scientists that mitigation strategies, reducing carbon emissions, have not been effective enough or fast enough to secure the fate of major coastal cities. We are now seriously considering engineering a solution at a continental scale.
And the most advanced and arguably most expensive concept on the table is the Seabed Curtain proposal.
The idea, spearheaded by glaciologist John Moore and his colleagues, is structurally immense. The concept is to install a flexible, buoyant curtain. Think of it as a massive, submerged sheet of industrial fabric.
How big are we talking?
Roughly 80 kilometers long, anchored to the seabed, and rising 600 meters high.
And its only purpose is to physically stop that fatal heat source.
Exactly. It would serve as an artificial protective ridge, physically blocking the deep, warm, circumpolar deep water from getting into those deep channels and troughs beneath Thwaites. The goal is to starve the grounding line of its heat supply.
And allow the ice to refreeze to the bed, slow the flow, stabilize the cork.
That's the idea.
The sheer cost of this project is staggering, but the proponents argue it's financially necessary.
The installation is estimated to cost between $50 and $80 billion, with annual maintenance costs likely running $1 to $2 billion.
But they quickly put that into context.
They do. It's a minute fraction of the trillions in infrastructure and economic output that would be lost by the inundation of London, New York, and Shanghai alone. It moves the discussion from can we afford it to can we afford not to do it.
And they're actually testing this.
They are. The sources highlight that field tests for the materials and design are planned for 2025-2027 in deep Norwegian fjords to prove the concept before moving to Antarctica.
We also see a variant idea, which sounds even more like science fiction, the bubble curtain.
The bubble curtain operates on a principle of density disruption. It would use massive volumes of air pumped from pipes laid on the seafloor.
And as the bubbles rise,
They disrupt the stratification, the density layers of the water column, preventing that relatively warm, dense CDW from reaching the ice base. But this system would require a truly massive energy input.
you need a power plant.
Potentially dedicated wind farms built in the hostile Southern Ocean just to power the compressors.
But these solutions, while they're technically innovative, they're fraught with complex ethical and legal hurdles. You can't just go and do this under the Antarctic Treaty System.
Absolutely not. Legally, any intervention of this scale occupies a massive gray zone. The treaty strictly regulates human activity and environmental protection on the continent. The political and legal wrangling over who pays, who benefits, who assumes the risk of failure, it could delay implementation indefinitely.
And the ecological consequences are also huge.
It could be devastating. Blocking nutrient-rich warm water, even if it is melting the ice, could radically alter the local marine ecosystem. These currents are vital for the local food chain,
So you could collapse populations of krill.
which are the base of the entire Antarctic food web that would impact whales, seals, penguin populations. It's an intervention with massive, unpredictable side effects.
And then there's the massive moral hazard attached to these expensive solutions.
This is perhaps the most serious critique. Critics argue that these highly visible, sophisticated techno-fixes distract political and public attention entirely from the root cause, carbon emissions.
It gives policymakers a false sense of security.
A dangerous one. It encourages delay and the necessary, painful mitigation efforts needed to decarbonize the global economy. I mean, the optics are terrible. We are debating spending $80 billion to build a curtain to hold back the ocean while we continue to pour greenhouse gases into the atmosphere.
The scientific data we've been reviewing, the speed, the structure, the cracking, the ocean currents, it was all collected by human beings working in arguably the most hostile, isolated environment on the planet. And that human element, it adds this visceral, almost terrifying dimension to the crisis.
It absolutely does. When you read the accounts of the researchers on the ice, they describe the auditory experience of the glacier's decay as deeply unsettling. The structural cracking, which we now know is accelerating, is constantly audible. They hear sounds like cannon shots or thunder as massive rifts suddenly open up in the ice shelf.
And these calving events, the fracturing, they're some of the loudest natural sounds in the entire ocean.
They are. They create noise pollution detectable thousands of kilometers away. And this constant, haunting acoustic bombardment, it serves as a physical, psychological reminder to the scientists that the very ground beneath their camp is disintegrating.
Which leads to this unique and heavy psychological toll. These are researchers documenting a catastrophe that will likely destroy their own homes, their own cities.
Peter Davis from the British Antarctic Survey, he captured that complexity perfectly. He described the work as bittersweet. The unparalleled thrill of scientific discovery paired with the profound dread of the results.
Knowing what they mean.
Knowing exactly what they portend. He admits to the absolute necessity of needing to disconnect from the reality of the forecast just to function. Because you can't come to work every day consumed by doom and frustration.
Ted Scambos, another veteran researcher, gave us one of the most vivid quotes. He said it's coming apart at the seams.
Right, comparing the structural stretching to tacky being stretched out until it breaks, that image of the ice stretching beyond its breaking point is just incredibly powerful.
And then there's that phrase that has become the summary of the crisis,
Yeah.
that Thwaites is holding on by its fingernails.
Yeah, while researcher Rob Larger clarified he hadn't personally coined the line, he readily acknowledged its accuracy in conveying the precariousness of the situation. It's the perfect, non-scientific summary of the urgent scientific consensus.
So bringing it all together, the core conclusion of the 2024-2025 assessment is stark, and it's unambiguous. The Thwaites system is entering a phase of irreversible structural collapse.
The analogy of the time bomb, it holds true across every dimension we've discussed. The fuse was identified in the 90s with radar. The explosive is the vast waves, primed by the retrograde slope geometry.
And the detonator is the spiderweb fracturing of the eastern ice shelf and the final failure of the pinning point.
The safety net of that ice shelf is structurally shattering and will, based on this new timeline, likely be gone within the decade. And once it's gone, the rate of ice loss will accelerate dramatically, driven by the merciless physics of that upside-down landscape and the constant mechanical input of tidal pumping.
We have moved past the quiet theoretical stage.
The system is no longer merely ticking, it is audibly, demonstrably cracking.
And that brings us back to the final provocative thought based on the source material. The unprecedented scale of geoengineering being actively debated and its price tag. It suggests that global leaders have accepted that mitigation has failed to secure major coastal cities, and that expensive, risky intervention is the only recourse left.
The question is this: what does it mean for society when the Plan B involves engineering a continent-sized problem at a cost of up to $80 billion, and yet that is universally considered the cheaper option compared to the damage? When the cost of saving London is measured in tens of billions, and that's a bargain, the map of 2100 will look fundamentally different from 2025. What coastal cities will you be planning for?